Welcome back. The topic of this lecture is routing. In particular, we are going to look at what is called intra-domain routing. First, we are going to look at the routing problem in general, and then we are going to discuss two routing algorithms, distance vector routing and linked state routing. By the end of this video, you would know how do we find paths between nodes in a decentralized manner. Both of these algorithms work without any centralized coordinator. In our previous discussions of switching and IP, we have seen several examples of forwarding. Forwarding is a different process than routing. Forwarding is relatively straightforward process as compared to routing. In forwarding, we simply select an output port based on destination address and a table that we call forwarding table. And in a forwarding table, an entry would contain mapping from a network number to an outgoing interface and some MAC address, right, such as Ethernet address for the next hop. However, routing is a process by which we build routing table, and this routing table forms the basis for constructing the forwarding table. And so the process of building a routing table requires use of some routing algorithm. And we are going to learn two such routing algorithms. And a routing table entry would contain a mapping from network number to next hop. Here is an example. This shows an entry in routing table and this one shows an entry in forwarding table. And so the first, this entry in the routing table is saying that in order to reach this network 18, the packets have to be sent to this router whose IP address is 171.69.245.10. And the corresponding entry in the forwarding table specifies which interface to send those packets to and what MAC address to use. Right, so this presumably is the MAC address of this router. We model network as a graph where the nodes of the graphs could be either networks, routers, switches, or they could be hosts. And the edges of this graph are links. Every link has some cost associated to it, and the cost reflects the desirability of using a link. So the lesser the cost, the more desirable that link is. Note that the cost, will not always, map to distance, which students are typically used to thinking about as the cost of an edge is basically the length of the edge. It's not necessarily the case in the case of routes in the network. And then the basic problem of routing is to find the lowest cost path between any two nodes, where the cost of a path equals the sum of the costs of all the edges that make up the path. For example, one can go from A to F using this link and the cost is 6. But then one can also take this path from A to E and then from E to F, and then the cost is 1 plus 2, which is 3. Alternatively, one can go through B, so A to B, then B to E, and then E to F, and then the cost is again 6. So here I have shown the shortest paths from A to all the other nodes. And as you can see, if we went from A to F using this direct link, the cost was higher as compared to if we choose to go through E. In that case, the cost is 3, and then the other alternative also gave us higher cost. And so how do we compute the shortest paths in a graph, right? That's the question that we are trying to solve. So one option is to do these calculations by hand and load them in some storage on each node, right? So that would be a static approach, but it has several problems. And for example, if there are node or link failures, right, this process has to be repeated. It does not consider the fact that we might want to add new nodes or new links. It also implies that the edge costs don't change, and that's not true. Edge costs could be a function of bandwidth or delay, and these parameters change over time. While this static approach might be acceptable for a small static networks, in general this is not the case, and instead we use an approach that relies on a distributed computation of paths. And these routing protocols are also dynamic. What it means is that these protocols are able to adapt to changes in the network. In this video, we are going to see two such algorithms. One is distance vector routing, other one is link state routing. Now, the complexity of these algorithms is of the order of n square to of the order of n cubed. And therefore, routing protocols that use these algorithms are they can be used in networks of, let's say, modest size, maybe hundreds of nodes, maybe a few thousand, but they are certainly not scalable at planetary or global scale. We use this term domain to refer to a network that is under a single administrative control. That could be a campus network, a university network, and so on. And so these networks are set to define a routing domain, and we use these protocols within a routing domain, and therefore they are also called intra-domain routing protocol. They are also called interior gateway protocol, or IGPs. In a later video, we will see an example of inter-domain routing protocol. Distance vector routing is called so because nodes share distance vectors with their immediate neighbors. Each node constructs a one-dimensional array containing the costs to all other nodes. Right? Some of the costs would be known to the node in the beginning. Others it will compute as the algorithm goes through different iterations, and then it distributes that vector to its immediate neighbors. And as I said, we have to start somewhere. And so the starting assumption is that all nodes know the link cost to each of their directly connected neighbors, and eventually every node would know the cost to all other nodes in the network. I'm going to use this example to explain distance vector routing. Note that none of these edges have costs written to it, because in this example we are assuming that cost of every edge is equal to 1. And actually the routing protocol that uses this is called RIP, or routing information protocol, also uses this assumption. So it's not that outlandish. However, I would like to note that this algorithm is generalizable, and it can work with any kind of cost that you can assign to different edges. So let's focus on this node A. Now remember, we had this assumption that every node knows the cost to reach to all these its directly connected neighbors. So the directly connected neighbors of A are B, C, E, and F. Right? So it's the first step is going to be initialization. So it's going to use the costs that it already knows. So the cost to B is 1, cost to C is 1, cost to E is 1 and cost to F is 1, right? And then D and G are not directly connected to A, and so it does not know the cost to reach to each of these two nodes yet, and so it's going to put infinity here. And then we also have this next hop, and so that says which node to go to reach the destination. And so since in the beginning all of these nodes to which the cost is known, they are directly connected, so we have identical entry in destination as well as next hop, right? So we to reach B we simply send it to B, to reach C we send to C, and so on. But again, for D and G it's not known because they are not directly connected. The initial distances that would be used by all these nodes A through G, they are summarized in this table. So for example, we already have seen the case for A. For example, let's consider D. It's D directly connects to C and G, and therefore we expect the cost to C and G to be 1 and all other costs to be infinity. Then, as we know, in the next step, each node sends its distance vector to its neighbors. So C is going to send its distance vector to A, F is going to send its distance vector to A, so is going to be the case with B and D. And so we are just going to focus on C and F because they are the only nodes that are going to change the distance vector table for A. So C is going to send its distance vector. So C is directly connected to A, directly connected to B. Then it's also directly connected to D. And then it's not directly connected to any other. So basically through C, A is going to know about D, right? So that's the only new information it's going to learn from C, because A of course knows about itself, it knows about B already, it also knew about C. And another information is going to come from F, right? So F is going to send information about G because F is directly connected to only A and G. A already knows about F, and so when F sends its distance vector, A will learn about G, right? So let's just go back and see. So as I said, C is going to send information about B and D, but just to keep this simple and not to clutter with too much information, we're just going to write the information that's going to make a difference. And so C is going to send information that it's connected to D with cost 1, and F is going to send to A that is connected to G at cost 1. And so after receiving these distance vectors, A knows that it can reach D, right, via C at the cost of 2, because the cost to C is already 1, and from C to D it gets the information from C, it's cost 1, and so therefore it's going to update this entry and it's going to put 2 because cost to D is 2 and next hop is C. And from the distance vector that it learns from F, it will know about G, right? So again, the cost to G is going to be 2, and it's going to be able to reach to G via F, and so the next hop is going to be F. And as you can see, there is not going to be any other change as far as A is concerned. And so this is the final routing table at A, right? So again, all these directly connected neighbors are reachable at cost 1, where the next and next hop being the same as the destination. and these two nodes D and G are reachable via C and F at cost 2. So finally, all these nodes A through G are going to arrive at this table. And it's an interesting exercise for you to verify, these entries. So we just begin with every node initial condition and all the distance vector that it receives from its neighbors, and eventually just try to come up with the correct numbers. The distance vector routing algorithm is also more commonly known as Bellman-Ford algorithm. So far we have discussed the distributed aspect of this routing algorithm. What about the dynamic aspect of this algorithm? And that is taken care of by sending periodic updates. Each router sends its distance vector to its neighbors periodically, even after converging. And then based on this periodic update, if there is any change, then the neighbor is going to update its own routing information. If a router fails to receive these periodic updates from a neighbor, that indicates that either there had been a node or a link failure. And if that is detected, then that results in another update being sent by a node to its neighbors. So unlike these periodic updates that happen every tens of seconds, so maybe 30 seconds, maybe few minutes, these are called triggered updates because they are triggered because of some changes in the network. Now we are going to see how distance vector handles link failures. So suppose this link between F and G fails. Before F detects this failure, in its routing table there would be an entry for G as G1G, where G is the destination, the number in the middle is the cost, and the last letter indicates the next hop. And so at A, the entry for G would look like G2F because this is the shortest path to G. And for C, it's going to be G2D, this path, and for D, G1G. Now, after this link fails, this entry at F is going to be modified as G infinity, and there is no next hop. And F is going to propagate this distance vector to A, and accordingly A is going to update its entry as G infinity. It does not have any path to G. Now A is going to get update about G from C and B also. And so actually, since the distance from C is less than distance from B, this update is going to make a difference. So just focus on this one. C is going to send this update G at the cost of 2. And so A's routing table is going to be updated as can reach G at cost 3 through next hop C. And then A is going to send this update to F, and so it's going to say G the cost 3 plus 1 is 4 less than infinity, so F is going to update its routing table as well. And now it's going to say let me write it fresh, so this entire thing becomes G4A. And so actually there is a path to G through A, so it's cost 1, 2, 3, and 4. And so that's how distance vector handles link failures. Distance vector routing suffers from a problem called count to infinity. And this problem prevents routing from stabilizing. So we'll try to understand this from the example that we had been looking for quite some time now. So now let's focus on this link between A and E. Suppose this link goes down. Before this link goes down, let's write down the routing table entries for E at these 5 nodes. So A's table would look like E1E. F's is going to look like E2A. G's entry would be E3F. C's entry would be E2A, and D's would be E3C. After this link failure, this is going to change to E infinity, and then A is going to send this update to its neighbors A, C, and also B, but we are only going to consider these 5 nodes here. And so this is going to be changed to E infinity. This is going to just go away, nothing. Similarly, C is going to change this to infinity, no path. And now suppose that C's update reaches to D before G's update reaches to D. So once C sends this information E infinity, then D is going to change this to E infinity, again no path. But then G is going to send its update, right? And it does to both of its neighbors. Actually, we are just going to focus on this one. And so as a result of this update is saying cost to E is 3, and so it's going to change it to 4 and then set the next hop to G, right? So that's how it's going to look like, E4G. And now something very interesting happens. So now D is going to send its update to C. C is going to change this to 5. Next hop D. C is now going to send this update to A, right? So A is going to change its routing table to the cost to E is 6, and the next hop is C, and then it's going to forward this to F. Now F is going to change this to cost to E is 7, and next hop is A. Then it's going to feed it to G. G had learned about E through F. It's going to update. It's going to update this to E8F. Then it's going to send this update to D. D is going to change this. Oh, sorry, running out of colors. Let's pick gray. And so it's going to change this to E, and then cost is going to increase. The next hop, everything else remains the same. So the cost is going to be 9, because the cost to E was 8. Add 1, 9. Going to send this update. So this cost is going to be increased to 10. Now it's going to change to 11. And then A is going to send this update to F. It's going to change the cost to 12, and so on. As you can see, this process will just keep repeating, and the distances are going to keep increasing until they reach very large value, right? And this is called count to infinity. And as you can see, it prevents the routing from stabilizing. There are some solutions to mitigate the problem. None of these actually fully solve the problem. The first is to use a relatively a small number as an approximation to infinity. And typically number is kept as 16. However, the problem is that if the network grows, this may not be enough. Then there is a solution that is called a split horizon. This is used in RIP. The idea is that when a node sends its updates to its neighbors, it does not send the routes that it learned from that neighbor back to that neighbor. For example, if B has learned this route E to A, right, through A, then it will not include this route when it's sending its distance vector to A. And then there is a stronger version of a split horizon. It's called split horizon with Poisson reverse. And in this case, B actually sends that route back to A, but it puts some negative information like, the distance to reach E is infinity. And therefore, A will never, use this route that, B had sent, which B learned from A in the first place. And I'd like to note that both of these are very limited fixes. They work only for loops that contain two nodes. The distance vector algorithm that we just saw is used in routing information protocol, or RIP. RIP uses hop count as metric. And in RIP, routers don't really learn the distances to other routers, but instead they learn the distances to other networks. Now, this is a packet format of RIP. As you can see, there are fields for network addresses. Right? So this is a typical entry for one network, and so there may be repetition. So here we have this diagram shows the route announcement for two networks. So there's net 1, net 2. It can go on up to, I think, 25 or 26 networks. And so the entries are the address prefix of the network, then mask of network, and then there may be a next hop here, and then distance to network. Right. There is also curiously a field for family of network. So RIP is designed to work not just with IP, but even other protocols than IP. In this example, D is going to announce to see that it can reach networks 3, 5, and 6 at cost 0, networks 2 and 4 at cost 1, and network 1 at cost 2. Similarly, C would announce that it can reach networks 2 and 3 at cost 0, networks 5 and 6 at cost 1, and network 4 at cost 2. Now we are going to look at link state routing. In the case of link state routing, the strategy is to send the routing information to all nodes. And this routing information contains information about directly connected neighbors only. Now, comparing this with distance vector routing, the routing information was sent to just the neighbors, and the information contained the routing information about all the nodes in the network. The routing information is exchanged using link state packets. A link state packet contains the ID of the node that created the LSP, the link cost to each directly connected neighbor. It also includes a sequence number, and finally it has a time to live field. Link state routing is used in OSPF and ISIS protocols. OSPF stands for Open Shortest Path First, and ISIS stands for Intermediate System to Intermediate System. Some of you might have recognized a problem with this strategy that is used in link state routing. The strategy says that we send this link state packets to all the nodes. So there is a little bit of chicken and egg problem. We are trying to figure out routes to the nodes, and we are saying that we don't know the routes, but we want to send to all the nodes. So how it is done? And the answer to that is that we use a routing. This is actually a routing algorithm in its own right, called flooding, and it's a very simple algorithm. So in flooding, we forward messages to all the neighbors except the node that sent the message. And flooding has some nice properties, like if a node is connected, it will always find it. However, flooding tends to be expensive because it sends redundant messages. So here is one example to illustrate flooding. So suppose this is actually a part of network, right? So there is some other node somewhere, let's call it node Y, and it sends some message, and this message arrives at this node X. Now, as the rule of flooding says, it's going to forward this message to all its neighbors except for the neighbor that sent the message, right? So there is going to be some other node here that sends this message to X. So X is going to forward that message to its neighbors A and C, right? And we are going to show these nodes that have received the messages with the blue color. And then A and C are going to send this message, right? So C received this message from X, so C is not going to send it back to X, but C is going to forward it to B. Similarly, A received this message from X, so A is going to forward it to B. Now B receives 2 copies of the same message, right? So that's the expensive part. And then B is going to send this message to D, right? Because B received this message from A, so it's not going to forward it back to A, or it's not going to forward it back to C, right? So at the end, all of these 5 nodes receive this message that was sent using flooding. In link state routing, LSPs are sent using reliable flooding. Let's say that there is a node, let's call it A. It's connected to another 2 nodes, say B and C. And then B is connected to D and C is connected to E, and on and on. That's it. So then A is going to send its LSP to B and C. So these are the only 2 directly connected neighbors using acknowledgements and timeouts, right? So that's the, so basically the LSPs are exchanged with the immediate neighbors using reliable transmission. And then after the next, immediate neighbors, the next transmissions happen using flooding. Nodes would store the most recent LSP from each node. Remember, every LSP has a timestamp, right? And let's just review what LSP has. It has an ID of the node that created the LSP, this link information, and then it also has a sequence number, right, as well as a time to live field. And so a node is able to determine the originator of an LSP, right, as well as when that LSP was generated, and therefore this step can be done. It basically compares its most recent LSP sent by that node, and if the LSP that it is getting is the same as the one that is in a store, it simply discards that LSP. Otherwise, it's going to update the previous LSP with the new one. and then it's going to forward this LSP to all the nodes except for the one that sent it. Similar to what was done in distance vector routing, in the case of link state routing, these LSPs are also generated and sent periodically. However, the interval between generation of two LSPs is much larger in the case of link state routing. So it could be several tens of minutes, could be even hours. And whenever a new LSP is generated, obviously the sequence number is incremented by 1. And when a node reboots for whatever reason, it will start at sequence number 0. Now the TTL field that is present in an LSP is decremented in two ways. First, when an LSP is flooded, a node is going to decrement the TTL before forwarding to its neighbors. And as a node stores the LSP, it also edges the TTL of the stored LSPs. And so when the TTL becomes 0, right, the node is going to flood that LSP and discard it. Now it helps actually when a node sort of fails for a brief time and then it comes back. So we saw that once it comes back, it starts at sequence number equal to 0. And so when it sends its LSP, the nodes would have LSP from this node that rebooted, having a sequence number that is larger than 0, and therefore they're going to discard this LSP. However, this step helps because once the TTL of the LSPs that are stored at these nodes become 0, this LSP is going to be flooded, right? And through this mechanism, this node that rebooted is going to get its own LSP at some later time. And after that, it can update the sequence number to be one larger than the last sequence number that it used, and so it can resume. Now we are going to see how route calculation is done in link state routing. So link state routing uses Dijkstra's algorithm to compute shortest paths. And so we are going to first discuss the Dijkstra's algorithm, and then we are going to use what's called forward search algorithm that is used in link state routing. So the Dijkstra's algorithm finds shortest paths from some node, some given node S, to all other nodes in the network. Here are some of the notations that we're going to use. So N is going to denote the set of all the nodes in the network. Then we're going to use Lij to denote the cost between nodes I and j, and in the case of Dijkstra, the cost has to be non-negative. If there is no edge that connects these nodes I and j, then this cost is going to be infinity. In addition to n, we are going to maintain another set M, and M will contain the set of nodes that we have processed so far. Right, so n minus M represents the nodes that we still need to process. And then lastly, Cn will denote the cost of the path from this source node S to a node N, right? So again, this algorithm is with respect to S. So we are not writing explicitly Sn, but it's to be understood that this cost is from S to N. And finally, node S will start the execution of the algorithm. What it means is that the first stage M is going to contain this node S. This is Dijkstra's algorithm, and we're going to understand this using this small example. So the first step is that we begin at node S, right? So we're trying to find the shortest path to all the nodes starting from A. So M contains S. Then we have to initialize the costs to each of the remaining nodes. In this small example, both of these are directly connected to S, so the costs to both of these are known to S. So C of A is 10 and the cost to B is 5. And then we go in a loop until n and m are the same. And so right now n has 3 elements, m has just 1. So in the next step, we add to m a node such that the cost of this particular node is the minimum for all the unprocessed nodes. Remember, n is all the nodes, m is the set of processed nodes, and minus m is the set of unprocessed nodes. So actually, let me just write this. So n minus m contains just these two elements, a and b. So out of these two, the cost of b is smaller than the cost of a, so we are going to choose b. And so in this step, which I'm going to write with green, m is now containing s and b, and then for each of the remaining nodes, still remaining nodes, so now n minus m just contains a, we have to do what is called relaxation. So we basically try to see if we have reduced the cost to the remaining nodes. And so C of A is going to be minimum of the original cost of A, which was 10, and the cost to the currently the current node that we are processing, which is B. So cost to B is 5, and the cost from B to A is equal to 2, and so that's 7. And so that is actually smaller than what was before, so cost to A is actually 7. And then in the last iteration, m becomes m union w, and there's only one node remaining, that's A, so m is now actually S, A, and B. There is not much to do, and minus m is empty, and that's when the algorithm terminates. So the shortest path from S to A now goes through B. Forward search algorithm is a variant of Dijkstra's algorithm that is actually used in linked state routing. In this algorithm, there are two lists that are maintained. One is called tentative, other one is called confirmed. And each of these two lists, tentative as well as confirmed, contain a set of entries that have this form destination cost next stop. We'll see an example here that would clarify what we're talking about. In this example, there are 4 nodes A, B, C, and D, and we are going to work out the shortest path from D to all these other 3 nodes A, B, and C. So the algorithm will begin at D. Therefore, we have to add D to the confirmed list. This is the initialization phase. Now from D, the cost to itself is 0. There is no next hop. It's itself. And then the newest node that we add to the confirmed list, we are going to look at its LSPs, right? And this node that we just added is called next in forward search algorithm. So D is the first node, but D is also the next node in this case. So we have to look at the LSPs of D. Now D is connected directly to B and C. So we have to add these two nodes to the tentative list. So the cost to B is 11. It's directly connected and it's reachable through B again because it's connected directly to D. Similarly for C, the entry is going to be C to C because the cost to reach C is 2. Next we look at this tentative list and we pick a node that has the smallest cost. So we have two options, B and C. The cost to C is smaller than cost to B, so we put C in the confirmed list and C becomes the next node. Now we inspect the LSPs of C. C is directly connected to D, to A and to B. At this time we add any neighbor of the next that is not in the tentative list to the tentative list, and then for the other neighbors that are in the tentative list we check for relaxation, right? So at this time, the tentative list has just B, but once we have added C to the confirmed list, because C's LSP would contain A, there is a new entry in the tentative list, and the entry is going to be, the node is A. The cost is going to be 12 because the cost to C is 2 and from C to A is 10. The cost to reach A is 12. And then next hop is C because that's how we are going to reach to C. And then for this other entry in this tentative list B, we check for relaxation. Now the original cost for to reach B directly through D was 11. Now through C it's going to be, remember the relaxation step, so it's going to be minimum of 11 or the cost to C, which is 2, plus cost from C to B, which is 3, right? And that's less, so therefore we take this, and so we update the cost to reach B as 5 and then next hop as C because we take this route to reach B. Next we look at the tentative list and we pick a node that has the smallest cost. In this case it's B, so we add B to the confirmed list, and then we inspect the LSP of B. So B is directly connected to D, to C and to A. Out of those, only A is in the tentative list, so we check whether we can reach A through B using less cost. And so we just check for relaxation here once again. So the cost to A was initially 12 because we were looking at this path. Now we have another possibility is from D to C, C to B, then B to A, and you can see that the cost here is less, it's only 10, but anyway we just go through the algorithm and we will get that automatically. So as for the relaxation step, it's going to be cost A is going to be minimum of what we have right now, which is 12, or the cost through this next. So the cost to B is 5, and then from B to A is another 5, and so that's 10, and therefore this is preferred path. And so basically at this step, only the cost is reduced, the next hop remains the same, because we are reaching A regardless through C. So earlier this implied that we go to C and then directly to A, but then after relaxation we figured out that the cost is less, but nevertheless the route goes through C. Now we have just one element in the tentative list, so this automatically is moved to confirmed list, and the algorithm terminates at this point. We are all done. We improve the scalability of link state routing by using what is called routing areas. So the idea is to divide the network into several areas. There's always an area called area 0. This is also called backbone area. And the idea is that LSPs are only exchanged within an area. So just to get some intuition into why this works, suppose we have 100 nodes. So if the algorithm takes, let's say, n cube time, then it's going to be 1 million. However, let's divide this into 4 pieces. So first network has 30, second 30, third 30, and then this area 0, let's say it has 10 nodes. And so now the complexity becomes order of n1 cubed plus n2 cubed plus n3 cubed plus n4 cubed. And so n1 cubed is 9,000, n2 is also 9,000, and then it's 1,000. So all in all, it's only 28,000. So basically by dividing this into smaller pieces, we improve the scalability. Now to make all of this work, there has to be some routers who have knowledge of more than one area, and they are called area border routers. So in this case, we have this R1 is an area border router because it's at the border of area 0 and area 1. And then R2 is an area border router. It's at the border of area 0 and 2, and then R3 is also border router. Packets go from one area to another area through a border router. So first they're going to cross this backbone area, and then from backbone area they're going to go to some other area. And so as I said, so LSPs are restricted to one area. So whatever is flooding, it's going on in area 1, that LSP is never going to be seen by any other router in any other area. But when we started out, we said that every router would know how to reach every other router. So how does it happen? It happens because these border routers then summarize the information they learned about the area, right, where they are sitting, to other areas. So R1 is going to summarize all the routes it has learned about area 1 to the other routers, R2 and R3, for example. And then once R2 has learned about routes in area 1, it's going to send that summary to the other routers in area 2, and so on. R3 is going to do the same. And so when R1 advertises these routes, it basically it pretends that all of these networks are directly connected to R1. That's how it's going to advertise the route. And so for example, for area 2, there are two border routers, R1 and R2. So they're going to advertise routes for different areas, and then it's up to the routers in area 2 to choose which router to send their packets to maybe in some cases, let's say if the packet is going from area 2 to area 3, it makes sense to send to R2, as opposed to if the packet is going to area 1, it makes sense to send it to R1. And the downside of this approach is that packets don't necessarily take optimal path. Maybe there is, let's say there is another area 4, and there is these two routers R5 and R10 are connected by a link. So there is a possibility that traffic that is leaving R5 can directly go to R10. However, because of this arrangement, it's first going to go to backbone area, and then from there through some border router, it's going to come back to area 4, although there was a shorter path available. To summarize, routing refers to finding the least cost path between any two connected nodes in a network. We saw that practical routing protocols rely on distributed algorithms, and periodic updates are used to deal with changes in the network. We saw two approaches to routing. First was distance vector routing, the second was link state routing. In distance vector routing, a node sends routing information about all the nodes only to its immediate neighbors. And in the case of link state routing, a node sends routing information about its immediate neighbors to all the nodes. For further reading, the topics that we covered are discussed in detail in Peterson and Devi, Chapter 3, Section 3, and Chapter 4, Section 1.1, and in Tenenbaum and Weatherall's book, Chapter 5, Section 2. That's all in this video. See you next time.